My topic, as you can see, is on stock and flow models of housing. This is an area that I have been working in for the past 10 years, and my studies have focused on the New Zealand housing stock. There are many reasons why stock and flow models of housing should be developed, especially within the context of sustainability. The benefits of housing are often overlooked or ignored. When all is said and done, it is ultimately the services provided by housing that are of primary concern to us. Housing in itself and the cost to sustain housing are but a means to an end. There is a dynamic relationship between the benefits and costs of housing, and these relationships can only be examined within the framework of a dynamic stock and flow model. Meaningful performance measurements of the sustainability of housing need to compare both the benefits of housing and the costs to sustain those benefits. Another advantage of stock and flow models of housing is that the flow of benefits and costs are measured as a true dynamic flux over time as compared to simply averaging the life cycle costs of a single dwelling over an assumed service life. Using the life cycle benefits and costs of a single dwelling can only provide rough estimates, which do not include the benefits and costs of an expanding housing stock. Realistic stock and flow models of housing should be driven by empirically established functions of mortality, otherwise they will be prone to gross error. However, in most countries there are severe data difficulties in estimating the mortality of housing stock due to the absence of suitable data over a sufficiently long period of time. In my PhD study some 10 years ago, I managed to establish the mortality of the New Zealand housing stock between 1858, the year of the first census, and 1978. I estimated the average service life of the New Zealand housing stock to be about 90 years. Of more significance, I managed to establish that the mortality of the New Zealand housing stock had been dynamic. Mortality had been a function not only of age, but also the expansion rate of the housing stock. In this graph, the cohorts or groups of dwellings which enter the housing stock over the same time interval have been scaled to 100,000 dwellings to enable easy comparison. The graph shows that each dwelling cohort has been subject to a different regime of mortality. The mortality of the housing stock had been more volatile than that of humans under condition of peace and absence of natural disaster. One implication of dynamic mortality is that if you try to estimate or forecast the replacement rate of housing by extrapolating from a data series of demolition, then your estimates can be prone to gross error. This is because dwelling losses over each time interval would not have increased in proportion to the size of the housing stock. Under conditions of dynamic mortality, dwelling losses can actually decrease even though the size of the housing stock continues to increase monotonically. A dynamic stock and flow model of housing is required to forecast the replacement rate of housing in New Zealand. Additional housing is traditionally supplied by constructing new dwellings. However, refurbishment of existing dwellings extend the service life of dwellings and thus provides an alternative source of additional housing. Investment in new housing as compared to investment in full and complete refurbishment of existing housing can be compared on a benefit-cost ratio basis. To do so requires a dynamic stock and flow model driven by realistic functions of mortality. As can be seen on the following graph, low discount rates facilitates full and complete refurbishment. In this scenario, annual maintenance costs increase from 1% of the costs to construct a new dwelling at the age of 0 to 2% by the age of 130 years. A maximum cost ratio of 0.5, for example, means that half the costs to construct one dwelling can be justified on refurbishment of an existing dwelling. Whether a dwelling is able to undergo full and complete refurbishment within the justified budget depends on the condition of the dwelling. Deferred maintenance would result in greater costs to achieve full refurbishment. A maximum cost ratio of 1.0 means that demolition and replacement can be justified. Low discount rates justify a higher budget and increase the likelihood that full and complete refurbishment can be undertaken within budget. Dynamic stock and flow models should be used for all energy and mass flow estimates of housing in particular and buildings in general, including wastage and recycling. There have been a number of studies to estimate the embodied energy content of a typical New Zealand house. Rod McDiarmid, a final year architectural student, estimated an embodied energy content of 2.6 gigajoules per square metre back in 1978. George Beard and Chan Aun carried out a more detailed study of a 92.9 square metre modal house in 1983 and came up with an embodied energy content of 3.6 gigajoules per square metre. Their study also included some rough estimates of the life cycle energy costs. In 2001, I updated Beard and Aun's 1983 study using Andrew Alcorn's 1998 revised table of embodied energy coefficients. My updated estimate of the embodied energy content was 2.75 gigajoules per square metre. I incorporated this update in a stock and flow model of housing, which included all the energy flows over the full life cycle of dwellings required to sustain dwelling services. This included maintenance, refurbishment, demolition and replacement. I estimated that it takes 10,000 megajoules to sustain 1 year of dwelling services provided by each dwelling within a housing stock after adjustment for economic depreciation of dwelling services. A substantial proportion of that energy flow, 17.4%, is required to sustain growth of the housing stock. The full benefits of this proportion of the energy flow is realised in the distant future. But if the housing stock undergoes continuous growth, then the energy flow to sustain growth is a constant cost. In another stock and flow model of housing, I've managed to make rough estimates of the past and current savings in the national cost to sustain housing due to owners undertaking refurbishment. The national savings have been in the order of 15%. There is the potential to reduce national costs by an additional 5% by undertaking additional cycles of refurbishment should the housing stock be stationary. However, the potential is inconsequential when the housing stock undergoes rapid expansion in the order of 2% per year. Programs to make more extensive use of refurbishment within a rapidly expanding housing stock are ineffectual because there are proportionately fewer older dwellings within such a housing stock that can take advantage of refurbishment. Reductions in the national costs to sustain housing requires a balanced combination of the levels of benefits provided by housing, the service life of components, and the life cycle costs to sustain the housing stock. In my most recent 2004 stock and flow model, I have estimated the benefit-cost ratio performance of a stock of lightweight timber frame dwellings in New Zealand. I have used proxies for benefits and costs to enable easy and meaningful comparison with other typologies of housing and housing stocks in other countries. The proxy for benefits are in dwelling service year equivalents, the dwelling services provided by a dwelling over 1 year adjusted for physical depreciation and obsolescence. The proxy for costs are construction units, the cost to construct one dwelling. Both proxies can be converted into dollar terms by multiplying by their respective prices. The current maximum benefit cost ratio is based on a housing stock that expands at the rate of 1.5% per year. This rate is the average rate of expansion in New Zealand over the past decade. The expenditure of one construction unit, the cost to construct one dwelling, can sustain a maximum of dwelling services provided by almost 27 dwellings after adjustment for economic depreciation of dwelling services. This benefit cost ratio has the potential to increase by 32% should the housing stock be stationary. As can be seen from this graph, if all dwellings in the housing stock had a service life of only 50 years, the minimum required by the current New Zealand Building Code, then the benefit cost ratio performance of the housing stock would be substantially less. It is of note that when the housing stock undergoes expansion, it is of little consequence whether houses are sustained well beyond the current average service life of 90 years. When the housing stock is stationary, it is a burden on society to sustain dwellings well beyond 90 years, especially if maintenance and refurbishment costs increase substantially with age. Future research includes closely examining the impact of using current land use succession criteria on the benefit cost ratio performance of housing for reasons outlined in my paper. A study of this nature applies especially to commercial buildings. The impact of current taxation schedules on the rate of demolition and replacement should also be examined. Current depreciation rates are somewhat arbitrary and are based on a much shorter useful life than is actually the case. The economic depreciation of dwelling services over the full service life of dwellings needs to be quantified. Most empirical studies are limited to the first 30 years of service life only, do not take into account the history of refurbishment, and do not separate the services provided by land from that provided by the building itself. Finally, it is well overdue to update the 1978 National Housing Commission study of the New Zealand housing stock. An update will enable many studies of the housing stock. For example, an update will enable estimates of the degree of mismatch of housing in New Zealand when baby boomers retire in the next 10 to 15 years and seek alternative housing.